square, and what is the mathematical dependency between all the postulates and all those things. Also, the no cloning theorem, a very basic theory, not really the detail, but a basic theory of quantum teleportation, as well as uh, a few of the Hermitian and unitary properties and all those things. And very primitive, like Hadamard and C0 quantum gates, we have seen and understood that how it works, what is the control, what is the target, and how to identify different quantum system with a different number of qubits as well as different number of quantum states. So our today's discussion is exactly the continuation of our last class, where primarily what I'm aiming is that today we will be covering a bit of more of the quantum gates, starting with the doubts or starting with solving all the 8 questions that I shared with you yesterday. Then we will start with the primitive quantum circuit design. We will try to take a very random quantum circuit, any random quantum circuit, and we will see that how the time evolution, with respect to the time evolution, different quantum states evolve, or how they behave differently. What is a qubit there? So how to interpret a quantum circuit? That is altogether what our objective is for today. Then we will look at into the very introduction to quantum algorithms and how it differs from the classical algorithm, and what are different types or operators in the quantum algorithm. There are different types of it. For example, say in classical we have like say dynamic programming. You can think it of as an operator, or say for example greedy, backtracking. These are all the different kind of algorithmic techniques or say types or say operator. Likewise in quantum also there are different such operator primitives are there for quantum algorithm, which we will look into that. Okay, so all of those variants we will actually try to cover today, or try to understand what do they mean. So with that notion in our mind, let us start. So this is the solution for the first question that I had given to you. I hope that few of you at least have tried the solution. So definitely, so this is the first circuit, if you see. So it was a 2 Hadamard gates. Already in yesterday's class, we discussed that it will be exactly the gate 0 that should come as an output. So it is basically whatever you give input, if you apply 2 Hadamard gates, you will be getting the same output. So 2 Hadamard or 8 square is basically acting as an identity kind of thing. Okay, so 2 Hadamard together, when applied just successively one after another, they behave as an identity matrix, as if whatever was your initial input, after 2 Hadamard, you will be getting the same out. And for that verification, I have given 1 and 2, both the examples. So in 1, you can see after a matrix multiplication and all those things. So just try to put this kind of vertical dotted bar. VP Madhurima, please check with others, or others also, they can inform if there is any voice break. Okay. Okay, thank you. Thank you. So after this time instance, so what do these vertical bars means is that how the time after different time instances, how the quantum states is evolving. So for us, it will be very good for you, or it will be very easy for you if we just do it manually and check how it works. So just try to put this vertical bar. So initially I'm starting with only gate 0. Once I apply an Hadamard, that is say for example, this is at T1. So at T1, I have something like this. Hadamard, this is a Hadamard gate, and this was your gate 0. So this was the matrix, 1 by root 2, 1 by root 2. Or you can equivalently write it down in this way, say 1 by root 2 times 1 and 1. Both are the same thing, right? So this alternatively also means gate plus. This is the same meaning. Okay. Now this is a T1. Now say for example, this is time instance 2. Now at T2, what will happen? At T2, you will be getting another Hadamard matrix, which is 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2 times your earlier output, which was 1 by root 2 and 1 by root 2. If you just multiply them, you will be getting a 1, 0. That is a gate 0. So this is verified, right? In that way, you can actually able to interpret these very basic quantum circuits. Say the second case was a plus. What does it mean? It is nothing but a NOT gate or an inverter, right? So if you give 0 just after this gate, which is a 1 qubit or a single qubit gate, that is why it is applied on only one line or one stream, whatever you call it. So you'll be getting a 1. Now after that, if you apply 2 Hadamard gates successively, what you will be getting? Say for example, this is at time t1. So at t1 you are getting from 0, it is 1. This is at t2 and this is at t3. So at t2, what you will be getting is a Hadamard on gate 1. What is gate 1? Column vector 0, 1. That's the dual of 1, 0. So it's 0, 1. So that is 1 by root 2 minus 1 by root 2. So which equivalently you can also write in this way, that 1 by root 2 gate 0 minus gate 1. Okay. And now if you apply on this result, if you apply another, say, Hadamard at T3, what will be your outcome? It will be, if you just multiply them, it will be again 0, 1, which is nothing but gate 1. So also this is verified. Okay. Now this is very fundamental. Okay. Now for those, I guess, I just want to show one thing. Just a minute. I want to keep the annotation so that it's there already. I'll be keeping all the annotations, don't worry. So let me just insert one slide here. Just a minute. Just wanted to show something. And okay. Okay. So yesterday I was discussing about this. So Hadamard 2 cross 2 is nothing but 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. Right? Now, if I just want to write Hadamard of 4 cross 4, I was telling it verbally, it will be this 2 cross 2 submatrix. Okay? So H2 cross 2 and a bar of it. So which is nothing but, say, 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. Okay? This is this one. Just a minute. Why it is not working? Oh, yeah. Okay. Now, the second one I want to work. So it's 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. Then the third one, which is 1 by root 2, 1 by root 2, 1 by root over of 2, and minus 1 by root over of 2. Third one, and the fourth one is the complement one, right? So it will be minus 1 by root 2, minus 1 by root over of 2, minus 1 by root over of 2, and plus 1 by root over of 2. Okay, so this is your H4 cross 4 matrix. Now, are you understanding that exactly how you can actually build H8 cross 8 and H16 cross 16 exactly in that way? So then you consider a 4 cross 4 submatrix, and whatever you have there, just copy for this position, and just at the bottom right, it will be every value that you have, the inversion of that. So plus will be minus and minus will be plus. Okay. Likewise, you can actually apply a 4 cross, like a 4 qubit superposition directly. And for a 2 qubit superposition, you need a 4 cross 4 matrix. Okay. So say for example, you have this, and I am applying this thing on, say, gate 0, 0, which is nothing but this thing. So this is a 4 cross 4 matrix, and this is a 4 cross 1 matrix. And what does it corresponds to? It corresponds to gate 0, 0, which is a 2 qubit quantum state, or also known as a pure state. And it is its corresponding vector, like column vector representation. No. Here the coefficient, what will be, how you are getting coefficient half? This is just a Hadamard matrix, just the operator. Coefficient is something that is associated with the quantum state. So here after multiplication, we look into the what will be the coefficients. Right now, we are not in a position to look into the coefficients yet. Let me multiply it. I hope you are asking that here it will be half in the H4 cross 4, which is not true. It will be exactly the way I have written here. But if you multiply it, That is, with respect to the resultant quantum state, you have to verify that what is the amplitude or what is the coefficient or associated with each of these terms. So let us do that. Let us do that. Say, for example, 1 by root 2 times 1, which is 1 by root 2. All these values will be 0, not to worry. Then 1 by root 2 times this thing, 1 by root 2 times this thing, all these values again, it will be 0. Then 1 by root 2 times 1, so it will be 1 by root 2, and here also it will be 1 by root 2. So if I just do this thing, it will be nothing but 1 by root 2 times your these things, that is 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Yes, so this is nothing but say 1, 0, 0, 0 plus 0, 1, 0, 0 plus 0, 0, 1, 0 plus sorry 0, 0, 0, 1. All the things together. This is just an application. This is just an application. Simple matrix multiplication. It is not exactly the one that I am doing. Okay, I got your point. What you asked, I got that point, but it is a bit difficult, like different, what you are telling. Now, say for example, I am doing something like this. 1 by root 2 ket 0 plus ket 1 cross this thing. I hope you are asking this thing. Okay, now this times say 1 by root 2. That is, I had initially 0, 0. Now individually I am applying a Hadamard and a Hadamard likewise. So in this case, I will be getting what? 1 by root 2 into 1 by root 2. So both the coefficients will come as common. Then it will be like say 0, 0 plus 0, 1 plus 1, 0 plus 1, 1, which is half into 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. See here, what I'm telling you is this will be a 4 cross 4 Hadamard matrix. That was my question, nothing else. So that was only my question, that if you have a 4 cross 4 Hadamard matrix and only one state was given to you, 1, 0, 0, 0 likewise, so this will be the output. And if I say you that I have a 0 and a 0, and I'm applying a Hadamard and a Hadamard, so what output you will be getting? Then the concept of superposed states come into picture, because individually these 0 will bring the 1 by root 2, 1 by root 2 kind of a coefficients into picture. But the simple 4 cross 4 Hadamard matrix looks like this. So the simple multiplication will give you this. So it depends on us what kind of quantum states we want to prepare. That it is. Okay. No, I am not claiming anything here. I'm not claiming anything here. See, this is the 2-qubit system. Basically, this is the 2-qubit system in a superposed state. Absolutely, there is no doubt about it. What I wanted to say is this is how a 4 cross 4 Hadamard matrix will look like. This is how you can expand a 4 cross 4 matrix. That is it. So consider it just as a matrix multiplication. But for your like normalization and all those things, just consider these factors, that if it has to be normal, all states has to be normalized and all. So this is how it will look like. So this was just as an example that how you can expand your 2 cross 2 matrix into multiple or more dimensional matrices. That was the only concept. So 4 cross 4, 8 cross 8, likewise you can consider. This is just a matrix expansion that I was talking about. You can also check maybe for the coefficients for these matrices as well. But if you want to consider the normalization and all, definitely here it does not hold because of the like same thing. It will not be 1. So 1 by root over of 2 whole square times 4, it will not be 1. So it will be this. So this is not a normalized state and this is a normalized state. That is what you can claim. But if I definitely give you this matrix and this multiplication, so it will be this one only. But your claim can be that this is not a normalized state because of the same thing. Normalization constraint does not hold. And here it is a normalized state. So it's a valid quantum state that you can think about. Okay, with respect to normalization, the last one will hold. Now, the third question was this. This was the circuit. Again, I am telling with respect to normalization. With respect to normalization, it has to be like the probability amplitude square. That has to be is equals to 1. Okay, the summation of that one should be equals to 1. Okay. So the third question was, you had a Hadamard there and this is a C NOT gate, right? And this was the output only. So let us just work. Say this is, say for example, T1, this is T2, and this is T3. So at T1, what you have? At T1, you have nothing but 0, tensor product 0. Okay. At T2, you have basically this 1 by root 2, 1 by root 2, and then yes, at T2 you have 1 by root 2, 1 by root 2, which is for the first qubit Hadamard product, this one, which is nothing but K0, which is till now it is 1 and 0. Okay, so the alternate representation of this one will be 1 by root over of 2 times K0 plus K1. This is the same thing. You can expand it in this way, and this is intact as it is. Okay, so this does mean that 1 by root 2 times 0, 0 plus 1, 0. Okay, now very carefully understand. Okay, the next operation. See the next operation. Next operation is a C NOT gate, where Q1 is the control and Q2 is the target. Now your question is, your question should be that how from these intermediate quantum state, how we can apply this C NOT gate. The answer is very simple if you know how to interpret the different qubit positions from this quantum state. So here, always remember, this is not first qubit and second qubit. It is not the way. This is a quantum state. But say this 0 or this position is for the first one and this is for the second one. Similarly, this is for the first one and this is for the second one. Okay. So likewise, so now qubit 1 was control, 0 was target. I have not explained Bell state yet. I'm just explaining it. And similarly for this case, this is the control and 0 is the target. Okay. This is the target. So for 0, there will be no change. So we will be getting, just a minute, we will be getting exactly the same thing, which is say 0, 0. And for the second case where 1 was the control. So since this is 1, so in second output or second qubit, we'll be getting another 1. Okay. How do we know which is control and which is target? From this position, from this circuit itself, we have to know. So this circuit represents, this is Q1 and this is Q2. So here it is your Q1, this entire thing is your Q1 and this was your Q2. And here in this state, say 0 is the first qubit, you can check, and this one is the second qubit. Similarly, this is your first qubit and 0 is your second qubit. So first qubit means Q1, second qubit means Q2, first qubit means Q1, second qubit means Q2. Okay. Now, since this is the case, so 0 will be the first qubit. So since it is 0, it will be Q2 exactly as it is. Here it was Q1, which is 1. So your Q2 will be Q2 bar, which is 0 has now become, this 0 has now become 1. This one I'm referring to. Okay. So this is Ket00 plus Ket11 by root over of 2. And now I am explaining you that this is a very basic example of an entangled state, which is also these two pairs are called entangled pair or maximally entangled pair, as we was discussing yesterday. And there are 4 possible Bell states. This is one of the Bell states. So what is a Bell state? Is nothing but an entangled pair of quantum states. So there are 4 possible Bell states possible, and this is one of them. 0, 0 plus 1, 1. What are the other 3? 0, 0 minus 1, 1, 0, 1 plus 1, 0, and 0, 0, 0 1 minus 1, 1. Likewise, there can be multiple Bell states possible. But this is a Bell state. So if you see, it means that if you have a 0 in output, for the first qubit, if it is 0, and qubit also will be getting a 0, or this class in probabilistic computation, quantum is nothing but a probabilistic computation. So class means basically that OR case. So, or if your first qubit is 1, second qubit will be in a perfect correlation with it and to give you the value 1. There can be anti-correlation of Bell state possible as well, which is, say, for example, 0, 1 plus 1, 0. So if you have a 0 at the first qubit, your second qubit will be 1. If you have a 1 at the first qubit, your second qubit will be 0. This is an entanglement, kind of a like mathematics for entanglement or Bell state or whatever you call it. Can you please explain T2, T3 part? Okay. No, T1, T2, T3, these are just for our calculation. No, we are just assuming because quantum like states are nothing but with respect to time, how they are like their evolution taking place. So how they are transforming with respect to certain Hamiltonian evolution or anything. So how they are transforming from one state to another state. So for that, I'm just considering that let us consider in this way that at time instance t1, what is the state of the qubit at say time equals to 1 for both the qubits q1 and q2. Similarly, at t2, what is the time, and at t3, what is the what is the quantum state of both the qubits at time t3. Now, after that, at T1 means when we have done nothing. So it's a 0 and 0 tensor product of that. Okay, so this is a tensor product representation. Tensor product form, say. So at T1, I have done nothing, right? So Q1 is also 0, Q2 is also 0. After time T2, no, that is also maximally entangled. That is also maximally entangled. Say 0, 0 plus 0, 1 and 0, 0 plus 0, 1 and 0, 1 plus 1, 0, they are thought of to be maximally entangled because there can be other cases where there is a not a like entanglement does not hold in that sense means, say for example, I have like taken something like this. So say I have taken something like this, say Hadamard, and say another one uh, where it is, okay, sorry. Okay, I cannot do it on the screen for this thing. Ah, I'm not able to use that space. Say, for example, I have a head of mud, and here also I have a C naught gate. So because of the head of mud and C naught combination, it is also entanglement, but it is just not the maximally entangled state. Because whenever it is entanglement, what is the minimum condition for entanglement? It has to be between two qubits. So when it is perfectly entangled, then in every instance, in between two successive qubits, you should be having the feeling of entanglement. But if that does not hold, so that is also entanglement, but maybe not maximally entangled state. But all the Bell states, they definitely like confirm the maximally entangled quantum states. Okay, so Hadamard and a C naught combination of them, I will be showing. So Hadamard and a C naught combination of them always will represent some sort of entanglement. Okay, first of all, just let me know. Uh, cannot be expressed as tensor product of pure state. What cannot be expressed? At what time instance you want to? What will happen if at T1 1 x1 T1 1 x1 means like you are asking if both the values are 1 1. AK jha. Okay. Let us take it. What will happen if both the values are 1 1? Let us do it. Let us do it. No issue. Let us do it. Just a minute. Just remember the same thing. Let us do it. Where I was here. Okay, here I was. Yes. So let me just insert one slide and like slide it will be so slideshow. Slide. So what you are asking is, what if we have something like this? If I'm not wrong, you are asking something like this, and just confirm. Is this the one you are asking? Okay. Let us start. So initially it will be 0. It will be 0. Say, let me plot it like T1, and then it will be T2, then it will be T3, and at the final end it will be T4. So at T1, what I am getting? Only 0 product 0. At T2, what I'm getting is both have been 1, 1 now. So 1 and 1. Great. At T3, what I'm getting, Hadamard on only the first qubit. This is the first qubit, right? And this is the second qubit. Okay. So only on one first qubit, I'm getting this Hadamard. So it will be this one. Let me expand it. So it will be 1 by root 2 ket 0, sorry, ket 0 minus ket 1. And this is only 1. So it is 1 by root 2 ket 0, 1 minus 1, 1. Okay. So this is the state of the quantum at T3. Now, right now, T4. So at T4, what will happen? This is always your first qubit as per the position. This is your second, this is your first, and this is your second. So it will be 1 by root 2 will be, I have nothing to do with the amplitudes for the C0 gate. So it is basically 0, 1, because this is control. Control is 0, so I will not do anything. Minus, this is 1, so I will change it. So I will make it 1, 0. So this is what will happen at the output state. Is it clear? So depending on whatever is given to you at every time, you have to expand it accordingly. Okay. So AK Jha, I hope. Okay. Okay. Thank you. Thank you for confirming. Okay. Now you will be. Just be a little patient. You will be definitely patient. Just we will also see it today. So the fourth one is say you have these kind of things. So this is, you have two qubits, Q1 and Q2. Whenever, see, why I'm doing it in this way is, whenever you will be seeing a random quantum circuit, so you'll be seeing very complicated quantum circuit with a lot of things. So that can be so complicated with, say, hundreds of such quantum gates, a lot of such quantum qubits into it, some ancilla qubits, some other like classical registers for measurement. So you will be unable to decode what do they really mean. So for that, before coding, because once you have a quantum circuit, they will also provide you the coding at the in the screen itself. If you just tell what is it in the quantum assembly language format, they will be given you. What is it in the Python language, they will be given you. So writing the code itself is not really very difficult thing in the era of ChatGPT and all those things. But the thing is, you should be able to understand that even after, no matter in what format it is given, whether it's given in the like programming language format or it is given in the quantum circuit format, both are equivalent exactly. You should be able to understand what do they really do or how the quantum state works. If you do not know this thing, then how can you write an algorithm for that? How you can make it work in that way? Because it is not really defined. No? So it is very new. So for that, you need to understand the fundamental of it, how it really works. So, I mean, please do not consider that this is not a practical, this is very theoretical, and only if you just do the coding in practical, you will be having an understanding. Say, for example, if I just write it down, say I'm just translating, though it was present here, here, I have put in these things. So this is only the code. Just consider this slide. So this is only the code. Are you able to really tell me that what is the final output if I even give you these 5 lines of code? Can you tell me that what will be exactly the output of any of these states? And if I want, I can also include some of the more steps into it. Say, for example, I'm writing, say, C phase Q1 and say Q3 after this C at 7. And then say again a C naught of, say, now Q3, Q1. So everything is very dependent. No? So only by giving you these things, you will not understand anything, what it is really doing. So I hope right now at least you have understood that why we need to do it in this way. Okay. So Hitendra, I guess you are asking. Okay. Okay. Some of the things will be there, you can follow in any website or something. But what really matters is what you cannot find in those websites. That is something that you should be learning. So yes, so this is the circuit. So this is a plus, which means right now, just check whether you are able to understand it. So this is ket 1 and Q2 is nothing. So it is basically ket 0 and I have 2 qubits only. Okay. So this is a Hadamard. So it has now become gate 0 minus gate 1, and this was your 0. Right then, C naught. Okay, I guess now it's very clear. The same thing, we are doing it. So this is another plane state. Okay, so initially it was gate 0 at T1. Both of them were 0. Say at T1, both of them are 0. At T2, your first qubit has become 1. Second qubit is right now 0. Then you are applying a Hadamard at T3. So it's this basically thing. So this one is nothing but the 1 by root 2 gate 0 minus gate 1. And this one is 0. So this is your second qubit, and this entire thing is your first qubit, which is in superposition. Okay. Now just follow in these steps. So it is from here I have written it. So just you do computation, apply C naught, you will be getting the result. Now, can you all of you try to construct at least one of these quantum states? 1 by root 2, 0, 1 plus 1, 0, or 0, 1 minus 1, 0. Any of these things. Can you just tell me what will be the difference? I'll come to the measurement thing later. As of for measurement, let us do it practically. When we'll just try to measure it, we will see how the different probabilities will come. Okay. Now, can anyone of you can tell me what will be the output, or like what will be the change in this circuit in terms of a quantum operation or anything, that if I want to construct these particular state, 1 by root 2, 0, 1 plus 1, 0. We can apply not get on Q2 in place of Q1. Not get on Q2. Just do the calculation. Just do the calculation, then you will see. You have already, like, from the earlier slides, you have a few constructions you already have done. Okay. For those who have already done, just hold for some time. Let others also take 1 minute for this. So 0, 1 and 1, 0. This is what I want to want. Either a plus or a minus. Okay, not to Q2. Okay, just shake it. Can I think it of in this way, that once I had these things, say 0, 0 plus 1, 1. I had this thing through the circuit. In question number 3, you can check that I had these particular steps, 0, 0 plus 1, 1 by root over of 2, right? So now I want to build what? 0, 1 plus 1, 0 by root over of 2. Now, after all the circuit is done, if at this stage I apply a NOT gate on qubit 2, will it work? I do not need to necessarily always apply a C NOT gate. I can also apply a NOT gate, a simple NOT gate. Like after this thing, on Q2, if I apply a NOT gate, then will my 0 will become now 1 and 1 will become a 0, which is the like second qubit. If I apply NOT on the second qubit itself. Yes, exactly. It will now become, because 0 will become 1 and 1 will become a 0. So in that way, see the solution. Initially it was this, a Hadamard, then a control NOT gate that was giving you 0, 0 plus 1, 1. Now I'm applying what? I'm applying another NOT gate, which is a simple, I've written also here, it's a simple inverter gate applied only on the second qubit. So this is your second qubit. You are applying only it on the second qubit. Remember, it's not, are there multiple ways to get the same result? Yes, that will be quantum circuit equivalence. Definitely, that can be possible. You can also think it of in that way. So if you're given, say, two quantum circuits, and if you just deduce it and just check the way we used to check for the whether the two Boolean expressions or whether they're equivalent or not. So exactly the way you used to do in a similar format, you can check over here. Just deduce it to the simple form or simplified, like simplest form. If that is true, or if for both the cases you are getting the same value, then you can call that, you can say that two quantum circuits are equivalent. Okay. So remember, it's not a C NOT gate, so we do not need any activated control here. So here it's a simple NOT gate, so simply a flip will work. Okay. So here only I have done a flip. a knot over here, and here another knot. And this one is as it is. Okay. Another was when I have a 0, 1, minus 1, 0. So we can start with this thing with 0, 0, minus 1, 1. We know how to construct it in this part, 0, 0, minus 1, 1. Now, if I just apply this, it will be now 0, 0, 0, minus 1, 1. So right now it will be 0, 1, minus 1, 0. Okay. So likewise, you can have different kind of quantum circuits if you want to design. Now, another just notation wise, you should remember that K0, K0, and K0, they are applied on 3 Hadamard gates. So this is at T1 and this is at T2. I just wanted to tell you different, some sort of like interpretations of these circuits. So here it will be, you will be getting 1 by root 2 times K0 plus K1. This is the status or fate of the first qubit. This is the second qubit. If any one of you are having any doubt in understanding that why this entire thing is a second qubit, why this is not a second qubit, please let me know. But these particular things should be very, very clear to all of you now. See, this was a pure state applying on Hadamard. This has become a superposed state only with respect to the first qubit. So this is the configuration or current status of the second qubit. This is the status of the third qubit. Till this point, it should be very, very clear to you. What do I mean by what? So this entire thing is the first qubit. Okay. Now, so 1 by root 2, 1 by root 2, 1 by root 2 because of the normalization thing again. So if you just bring it outside, so it will now become, say, let me multiply 2 by 2, 2 cross 2 way. So it's 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And this was only your K0 plus K1. Now, if you again multiply it, you will be getting all the possible values. Now, whenever I am writing it in this way and whenever I am writing it in this way, what is the difference? Just understand the difference in two different forms of representation. Here, this was your first qubit. This was second qubit. This was your third qubit. When the entire thing is represented in the tensor product form. But here in this case, whenever you are writing it, multiplying everything, there is no tensor product thing here. So after all these things, this is a simplified form. Say, for example, this is a simplified form. And here, now this is your first qubit, this is your second qubit, this is your third qubit. This is first, this is second, this is third. This is first, this is second, this is third. This is your first, second, third. First, second, third. First, second, third. Similarly, first qubit, second qubit, third. 1, 2, and 3. Where 1 represents Q1 or qubit 1. 2 is for Q2 or qubit 2. 3 is for Q3 or qubit 3. Okay. Now, if I just give you any complicated circuit, no matter what I give it to you, sorry, where it was, I guess here. Okay. Here. Yeah. If another, say, for example, Hadamard, if I give it, now, say I have done like something like this. Now on this again I have applied on Hadamard. Say for example there is another gate. Let me just for now write it down. Say Z and control Z. Say likewise. Post that another Toffoli. So likewise I can build up any random quantum circuit. But once you have an understanding that how the qubit 1, 2, 3 their evolution is taking place, you should be able to tell me. You should be able to tell me. And if I just want to write, just remember this circuit, we will be also writing it in that form, like programming language form, as Hitendra was mentioning. Okay. Now, this is another one. The same thing. What is the difference? See the difference here. Okay, one was asking for the previous slide. I guess this was the previous slide. If you're having any doubt, you can ask. Otherwise, you can check it later. So this was your previous slide, that is Hadamard, Hadamard, and Hadamard. Likewise, now, if I just give you Hadamard, Hadamard, and in the third qubit, it is nothing given to you. No Hadamard is given to you. So how you are able to interpret the output? Okay, so you can do it in this way. So on first qubit, you are applying an Hadamard. On second, you are applying an Hadamard. On third, you are applying nothing. So it's a basic pure state. Can we do that? Yes, we can do that. So now it will be half 1 by root 2 times 1 by root 2, that is half, into 0, 0 plus 0, 1 plus 1, 0 plus output of the circuit that you draw now. You mean this thing? This thing, the big circuit you were asking? Uh, I guess you are asking the same, Dr. Sanju. Just a minute, just wait. Let me complete it. Then I will come back and draw this one. We will do that. No issue. So now it's half, that is multiplication of 1 by root 2, 1 by root 2. Now this entire thing. Okay. 0, 0, 0, 1, 1, 0, 1, 1 times this thing. Now just a multiplication again. So it's basically a product form, 0, 0, 0 plus 0, 1, 0 plus 1, 0, 0 plus 1, 1, 0. Also check that in this way, any random quantum state actually we can represent in the mean term format, or whatever is there in the mean term and max term in the Boolean expression. I hope all of you remember that one. So that we can actually express here as well. So with respect to some very like combinatorial expression, whatever you have in classical, we can actually express it. If we just express it in the min term or max term or SOP or POS form, we can actually represent it in the with respect to certain quantum circuit. That is why quantum circuit is like thought of like kind of a supervised circuit or superior circuit than a classical one. So this is nothing but a min term of 0 to 46. If we just ignore the like magnitude. Okay. Now, similarly, it can also happen like in this way. Say, for example, on first and third qubit, I have zero Hadamard and nothing on the second qubit. That is also possible. Okay. So it's the first qubit, then this is the second qubit, this is the third qubit. Now, once I do these things, just do the calculation and checking all those things, then you will see 0, 0, 0, this min term form you will be getting. This SOP form you will be getting. Okay. Just you should be very like well versed with the language of quantum circuit. And since it can be represented in different forms, you should be able to interpret those multiple forms. This is another one. This was the 8th example. Here it is at T1, 0, 0, 0. I'll not put much time for this. You should be able to now understand what it is. So this Hadamard on first and third one. So this one is the thing. Just okay. Here the ket one is missing, and here also I guess yes. Okay. And then it's a Q1, Q2, Q3 at this instant. Till this part, at least it should be very clear. Then at T3, what I'm doing a C0 on Q1 and Q2. So C0, Q1, Q2. What it will do? So Q1 is the for control, Q2 is the target. So 0. Initially, it's like a 0, 0, nothing will happen. 0, 0, nothing will happen. 1, 0, so it will now become 1, 1. Yes, it is true. And then 1, 0, 1. So 1 and 0, it will become now 1 and 1. So 1, 1, 1. So this is on application of C0 gate on Q1 and Q2. Q1 is control and Q2 is target. Similarly, if I just apply it on Q2 and Q3, it will become, considering Q2 is the control and Q3 is the target, it will become now 0, 0, no change, 0, 1, no change, 1, 0, yes, make it 1, 1, okay, I have done it. Then 1, 1, okay, then make it 1, 0, I have done it. So this is the final output that I'm getting. This is the final output that I'm getting. Okay. Say another quantum circuit I have just written. What if we have two qubits with two edge gate with each versus we have a big Hadamard gate? No, I told this thing that big Hadamard gate. See that H cross 4 cross 4 matrix was how just I can make it from a 2 cross 2 to 4 cross 4. Ignored it. But writing it in this way in quantum circuit, real quantum circuit means nothing but the breakdown. You can think it of in this way. So both are equivalent. So just break it down in this form and then do your calculation. It does mean the same thing. It does mean exactly the same thing. It means that you have to first apply, you have to apply Hadamard on both the qubits. That is the thing. And there, I applied a Hadamard matrix on entirely a 2-qubit state. So those two things are very different. Okay. So there, and definitely it was not normalized. But in this case, it will be normalized. Yes, you can do that. This is a fantastic question. You can actually do that. Now, someone has asked very beautiful question. That is, if I am in a particular state, can I just reverse back, go back? Exactly, you can do that. Exactly, you can do that. So whatever you have done, just follow the same thing again. So let's do it as a homework, or we can also try it today. So whatever you have, say for example, for this circuit, it will be, say, Hadamard in this way. Say Hadamard. So how the circuit will look like? I'm just drawing that thing. So this is this. This one will be this one, and so how that is why it's called reversible, right? So you can definitely do that. So this is a control target now, and this is a control. So you have till this point, right? Now just try to do the exact thing in the reverse way. So again, do the same operation till this part and from here. So now it's, if you do this, this is the, say, do operation, and this is the undo operation, undo computation. We'll be getting the same thing. Just check it. Just check it. If you do it, you will be getting the same thing. Just like that is why, just like if you have two Hadamard, you are getting the same thing. Here, there is no equation or no operation, but it is exactly the same. Say, for example, NOT gate, another NOT gate, you will be getting the same thing. Say Hadamard gate, then say, let us try with a small thing. Say this. Then again a Hadamard. Just check what it will come. Say here it is 0, here it is 0. So at this point, what you got really? You got that 1 by root 2 k 0 0 plus 1 1. Okay. After that, what I'm doing, I'm applying an Hadamard on what? On the first qubit. Okay. So first qubit will now become, again, I will apply an Hadamard. So just for simplicity, okay. So first qubit will be Hadamard. Means, again, just for simplicity, let me write it down in this way. Okay, I cannot do it over here. So it will be, say, 0 0 plus, from here it will be 1 0 plus, again this one will be, 0, sorry, 0 1, and here it will be, okay, just a minute, wait. This is a 0 1, and this one will now become an Hadamard on this qubit. So this is a 0 1 minus 1 1. This is what you are getting. Now if you do a measurement in first qubit, you should be getting, so first qubit is giving you nothing but, say, 0 0. Okay. Okay, somewhere maybe I'm just missing. Just hold it for some time. Just hold it for some time. Let me do it. 0 0 1, and then it is the second qubit, where it is, say, I'm doing somewhere, I'm just doing the wrong thing over here. Maybe because of the head amount, it will be different. Okay. Will it happen if you just apply the C naught gate? Just do the, again, apply a C naught gate and just check whether it will be getting the same thing or not. Just do it. All of you, just do it. Maybe I'm missing out somewhere. Like 0 plus 0. It is coming 0 plus 1 0. Forget about the amplitude. And this will be, this 0 will be 0 1 again, plus 1 1 with that amplitude. If I now just apply an Hadamard, yes. If I now apply an Hadamard, I'll be getting the same thing individually. So it will be this thing I'll be getting. 0 0. Yes. Thank you. Thank you. I just missed the C not get. I just missed that one. Okay. Yes. So you have verified that you can actually do that. Sorry, I just missed this one. And also for if you're having any doubt in understanding this, so after this thing on Hadamard, it will be nothing but H on second CL on first and second on third and second again on fourth. Okay. I don't know what you have written. Maybe you are just telling the same thing for some other circuit. Yes. Yes, definitely. Definitely. So this is basically nothing but this 1 1 1 1. Now you get, if you again apply an Hadamard, it will be again this thing like 1 0 0 0. You will be getting it. And the 1 0 0 0 is nothing but you can also represent it in this way, like get 0, tensor product, get 0. Yeah, the same thing. Okay, okay. Now we were in this circuit. Let us consider this circuit. Just one thing. Should I be keeping annotations for all these slides or I should be removing it? Because this is making the slides a bit clumsy. But if you want me to keep these things, I can also keep. Remove. There is a mixed reaction. So, okay, keep it. Okay, I will be keeping it. Even if I do not keep it, you will be going to the recording, you will be getting it. Okay, that is so much of an ask. Okay, okay. Let me just complete this one. Then we will see. Then we will see, definitely. So say another quantum circuit. Say another quantum circuit. Red color we can distinguish. Yes, you can definitely distinguish. No issue. That is why for few slides I have taken another blank page. Okay, but while describing these things, like emotionally only I had written over here. So sorry for that. But anyway, or you can keep a screenshot because this slide looks very clumsy. At least for this slide, let me remove it. So for other slides, because initially the slides were quite like easy ones and like red and blue was not this much of clumsy. So I will be keeping only for this slide, just keep a screenshot at the end. Okay, only for this slide. So say we have another quantum circuit, which is like this. What is the new thing introduced in this particular thing? This is a Toffoli gate or a C square NOT gate. Also another one thing, if you notice, this is a C NOT gate where I have placed the control here and the target here, which I mentioned in the last class also that we can do something like that. So at T1 it is 0 0 0, T2 till T4 I will not tell you anything. So till T3 is basically what already we have seen lot many times. So T4 is CC naught, that is controlled naught of Q1, Q2, Q3. So now your Q1 and Q2 both are control and Q3 is your target. So just see it over here. Both the things should be 1. So when it is happening only for the third and fourth cases. So it will be now 1 1 0 will become 1 1 1. The third qubit will be flipped. And 1 1 1 will become 1 1 0. The third qubit is flipped. Okay. So this is a basic Toffoli gate. And last one is another C naught gate where Q3. Just see the kind of representation that I've given over here or syntax. First thing, first argument that you write with respect to C naught is your control always. So do not mess up things. C naught Q1 Q3 is not equals to C naught Q3 Q1. C naught Q1 Q3 means Q1 is your control, Q3 is your target, whereas C naught Q3 Q1 means Q3 is your control and Q1 is your target. Accordingly, we have to calculate. So here, what I mean is Q3 is the control. Q3 is control. Or sorry, here Q3 is control, Q3 is control, and here Q3 is control and Q3 is control. So of course, for this and these cases, 1 and 3, 1 and 4, nothing will happen. For 2 and 3, what will happen? Since Q3 was 1, Q3 is 1, so you will make your Q1 as 0 to 1. Similarly, here also Q3 is 1, so make your 1 from 1 to 0. Done. So this is your final quantum state. Okay. Okay. For those who want to take a screenshot, now you can take a screenshot. Where let me just yes. So this is the do and this is undo computation. That is why quantum is also called reversible circuit. So the same set of operations, exactly if you repeat in the reverse order, it will be reversible. It will be like the same thing that will be getting us out. So please take the screenshot if you want to. Pointer big. Screenshot only to the slides and then remove. Oh, I will be adding the screenshot itself. Okay. That also. Okay. I will do the addition later. As of now, let me just, for this, discard the annotation for this slide. I have taken the screenshot. I will add it. I don't know why I'm not even like able to find out where my normal mouse pointer is at times. Where is it? Okay, yes. Okay, I will add it. Just after this thing, I will add it. Oh, there is a blank slide, so here I will be adding it. So 4, 7, okay. All these things are gone. Great. So 9 also. Sorry for that. 10, 11. Okay, anyway. So I will add that one, the bigger one. Yes. Just after that, let me add a new slide here where I will be adding this thing. The screenshot. Okay. Now this thing. Okay. Okay. So this is the equivalent. This is the equivalent kind of this thing. Like the quantum computing language, or say the programming languages that you can have. Now again, this is very simple. This is little bit abstract, but when initial times like 2014, 15, 16, at those times we used to follow these particular language in order to code do the coding with respect to a quantum computer. Right now it's even simpler than this, but generally if you know this format, in any format, be it like Rigetti or say Qiskit, IBM Qiskit, or say some other programming languages also, like SAR, Google SAR, you should be able to understand at least what do they mean, because the fundamental things will be same only. Okay. And most of the platforms also provide the equivalent form. So just write it down. If you just drag and drop and like build your own quantum circuit itself, it will provide you the entire Python code by itself. You do not need to do anything. Just do a certain, and in real time, you just do a modification with respect to your quantum circuit as and when you want to. So everything after that will be automatically built. So that is very easy. So here unnecessarily the coding constructs and all in Python, we don't need to manually learn it. So how we can code it? So here it's a like Q1, Q2, and Q3. So it's a head amount on Q1, head amount on Q3. Now you know these things. So it is basically C naught Q comma Q1 comma Q2, where Q1 is the control, Q2 is the target. Then it's C square naught or CC naught, or you may also find it in the name of Toffoli. All the meaning are same. So C square naught, then Q1, Q2, Q1, Q2, Q3. And then it is another C naught where Q3 is the control, Q1 is the target. So it's C naught, Q3, comma Q1. So these are the sequence of quantum operations for a 3-qubit quantum system. Likewise, be it like very long, that is not a problem. You should be able to tell that what is the or how we can build the circuit. Do I need to really draw a very big like quantum circuit and do these kind of things? What it is and how? I don't think that is necessary. Okay, okay. So be it whatever, just do it like one by one step by one step, then you will be able to understand. Okay. Now there are a few more things. I was thinking to give you break after this. Just give me some more time. Yes, okay. Here I put a few for the slides. Okay. Let me just complete a little more of the quantum gates. So then some of the quantum circuit and its language we will be able to like decode in a very easy way, or any language we can do. So from these itself, I'm telling these are like single qubit Pauli matrices, Pauli gates or Pauli matrices. Say for example, could we go to previous slide? Yes. Okay. So these are Pauli matrices. X is nothing but the not Pauli. X is nothing but your very well-known NOT gate. This is why this is not very commonly used, but still you should be knowing it. And this is Pauli Z, which is only in this position, it is a -1. So it is also like a, this is Pauli Z is also known as a phase gate. Phase gate. Or a Z gate, whatever you call it. And just remember with this, with respect to this, like Pauli Z and control Z, they are almost same. Just this was initially Z and this is a control Z, CZ, let's say, for example. So CZ means a control Z. That is a controlled not controlled Z gate, just like initially you had your NOT gate and C NOT gate. Right now you have your Z gate or a phase gate and a controlled phase gate or CZ gate. Okay, so initially for C naught, what was your logic? If your control is 1, so please just flip your target. That was your logic. So here for phase gate and control phase gate, the logic is if you're having a 1 as control and if your target is 0, then do not do anything. What I'm telling is, say for example for CZ, your control and target. These can be the two variables, right? That is why it's a 4 cross 4 because you need 2 qubits at least. So if your control is 0, then definitely nothing will happen to target. So this is not applicable. NA. If your control is 1 and your target is 0, so just make it 1 and 0. Nothing will happen again because your target itself is 0. So how to change the phase of 0? Nothing you can do. But if your control is 1 and your target is also 1, then you make your target as -1. That is, you just need to change. If it is 1, you just make it now -1. Okay, so absolute 180-degree phase shift will happen. Okay, so just remember this is very useful gate. Few of the gates are very useful. I'll be marking it. So Hadamard Z, Hadamard, Pauli Z, Pauli X, because Pauli Y is mostly not very widely used. Theoretically, it's like you can remember it. Control NOT gate, I don't need to tell you how much it is useful. Toffoli as well. It's fundamental for any logic build-up. It's required. This is very generic. So instead of all these gates, I will tell you to remember only this thing. 1, 0. So it's 1, 0, 0 e to the power I theta. Where depending on your theta, you can devise what is what. For example, if theta is say 180-degree, theta is 180-degree, then what it will be? Or pi. Then what is the value of e to the power I pi? It is nothing but cos pi plus I sin pi. Right? Euler's theorem. So cos pi value, what is cos pi? 180 minus 0. Likewise, if you compute, it comes to what quadrant if you check it? So it will be negative. So it's minus cos 0. Cos 0 value is 1. So it will be minus of 1 plus I times sine in second quadrant. It's basically it's 180 minus theta is 0 minus sin theta. So it's 0. 180 minus 0, so sine 0 is 0. So likewise, it is minus 1. I don't need to tell you. I think all of you know that e to the power I pi is nothing but minus 1. So that is why for, see, this is a normal, any kind of a phase gate, anything, normal gate with theta. So on that, if we just put the value of theta is equals to pi, I get my phase gate or Pauli Z gate. Control Z is nothing but a control gate operating on top of the Z gate. Okay, depending on the value. See, even I also do not know what is the difference. I do these things seem because I do not remember it in this way. So I only remember the generic form. Whatever be they want to give the angle to be, I just put the value. So there are likewise there is T gate, S gate. All those things are like thought of. Sort of maybe it's like just put your value of theta to be pi by 2. Just check what is the value. I guess it will be I, if I'm not wrong. Just put your value to be e to the power I into pi by 2. I guess it will be cos pi by 2, which is what? So 0 plus I into sine pi by 2, which is 1. So it's e to the power I pi by 2 is nothing but I. So likewise, they have got their S gate. Okay. If you just put some other value of theta, it will be another value. So t is nothing but, I guess, a certain kind of a pi by 4 or pi by t. You don't need to remember these things. So whatever be the theta, just put the value of theta, apply Euler theorem, you will be able to know that what should be the matrix that you should multiply before your quantum state. Simple thing. But what you should definitely remember is how a Hadamard, how a NOT gate, how a C NOT gate, how a like Toffoli or a C square NOT. C square NOT does not mean that only you need to know C square NOT. Rather, you should be knowing the C to the power N NOT gate, anything, or how you can actually make it bigger. All those kind of control, NOT gate and phase gate. That concept should be very much clear to you. And one more thing is remaining. Hadamard is very fundamental. You definitely need to know it. And another gate is very also like one of the very primitive gate, that is swap gate. So in swap gate, first few things you should be remembering it, that how you represent it, and also just take this column, that how they are represented. So Pauli X is nothing but X or not gate. This is simple X. This is Y. This is Z. Z means Pauli Z or phase gate. H is Hadamard. S is, forget about S and T. This is controlled knot, where the field bubble is basically control and this plus is your target. Now, similarly, in C square knot, it is like 2 control and 1 target. C1 and like Q1 and Q2 control and Q3 is target. All of these things you know. Just what is new here? The new is control Z, which is, say, control is a field circle instead of a target, which is a plus or a XOR symbol. Here now it is this thing. And this alternatively, equivalently also is represented using this. So whenever you have two field circle, it is a control Z gate, just remember it. And whenever, though it's a little bit of like complicated representation, why? Because here which is control and which is target is not very clear. So of course, there should be certain indication. So please follow this particular symbol. Otherwise, just go for the conventional thing. The first one is your control and second one is your target. And another one is a swap gate. So for swap gate in the quantum circuit itself, you can see either of these two representation. Generally, this representation is seen. Okay. So this representation means that contents, remember, contents present in the qubit 1 and 2 will now be swapped. So it is basically the Q2 will now become Q1 and your Q1 is now become Q2. If you want to think in this way, see, generally C naught gate is thought of to be like equivalent to certain sort of XOR gate. Give me a just 1 minute, please. Give me 1 minute. Yes. Sorry, very sorry. So the first one, yeah, what I was telling that yes. So generally the C naught is thought of to be equivalent to XOR gate. And in case of these swap kit, you can remember that whatever the content is just shared. Just see it like 00, it is a 00 only. And 11 is 11 only, because both are having the same content. Okay, qubit 1 and qubit 2. But here the content present in 01 will be now into like 10, and 11 will now become 01. That is the thing. So for 10 you are getting a 1 over here. For 01 you are getting a 1 over here. And this, the last matrix for C² not, already you know this one. So just check it. Here only you can see a NOT gate, right? Here only you can see a NOT gate. And till this part, it is basically the identity matrix. Okay. So I just keep these things for further, like say, discussion. Can use something. Just a minute. Say for example, okay, let T-gate. T-gate. Yes, T-gate is just T-gate is 5/8 means you just need to change the angle here. I just mentioned that, okay, you just change and your angle theta accordingly. You just see the manual. See the manual what it is. But if, for example, for few cases, definitely we actually fix it in that way that it should be always like pi/4 degree rotation for all the subsequent steps. There we need some specific gates. That is. And often it is like, say, pi/2 degree rotation. Often it's like 180 degree rotation. Likewise, we define these gates, but generally it is e to the power I theta, where theta is the generic representation. If you just put the values of theta to be any one of these values, you will be getting it. Okay. If this is okay, let me just take a 5 minutes break for all of us. Then we will start with one quantum circuit followed by quantum algorithm. Okay. So whatever be the time, just come back after 5 minutes. What is the time now? Let me see. Let us come after 5 minutes. It's 3:50, so we will start at 3:20.
Sure, ma'am. Thank you, ma'am.
Thank you. Thank you. We start now. 332 it is, 322. Okay. Yes, thank you. Yes. So I told that we start with some examples, more examples of quantum circuits with all these kids. We put Hadamard gate on 000. Okay, this is this thing only. We have to do it in this way. So it's 1 by root over of 8 times 000 okay? 111. Okay. Now uh it can be anything. So let me just draw it in this way. Say good. Okay. Okay. Say for example like this. Yes, Toffoli, C naught, phase, control phase. Yes. Okay. So instruction wise, it will be like what? It will be like first I have to write it down, say Q1, Q2, Q3. Often in cases it can also be written like capital Q1, likewise in any way, or say capital Q1, or I'm as of now I'm writing Q1, following this thing. So Hadamard, first operation is Hadamard of Q1, second is C naught on. First is, of course, like introducing the registers. So this is at the 0th phase, all the Q1, Q2, Q3 with respect to 000. First is that one. So after that, the quantum gates will start being operated. So it's Hadamard on Q1, then a C naught on Q1, Q2. Then third is a Hadamard on Q3. Fourth one is a C square naught or a CC naught on Q1, Q2, and Q3. Fifth one is a controlled phase gate. So it's basically a CZ gate on Q2, Q1, right? Post that, it is a swap gate between what? Q1 and Q2. Then it's a seventh one is a Z gate or a Pauli Z, whatever you call it, on say Q3. Okay. So these are all the list of quantum operations. Let me put first time. Otherwise, it will be difficult. Can I just change the color? यहाँ क्या होता है ना कुछ color वाला. Let me choose this color. Yes. So this is say T1. उसके बाद यहाँ पे T2 followed by T3. Then it's a T4 or T5. Then T6. Then it's T7. And at the end, the final output you will be getting at T8. Okay. So at T1, what is the state? Get 0, CZ, Q2, Q1. CZ, Q2, Q1. Na? CZ, Q2, Q1. Sorry, what was your question? CZ, Q2, Q1 and CZ, Q1, Q2. Just write it in chat again. Otherwise, I need to again change my screen and all. Are they same? Yeah, Q2, Q1, of course, they are not same because whenever I write, I'm writing Q2 first, then it means that Q2 is the control and Q1 is the target. Okay, but it is not with respect to NOT gate, rather it's respect to the Z gate. Let us see. Let us see how it works. So at T1, it's gate 0, gate 0, and gate 0 because I have 3 qubits. So it's always we will start with this notation. So then it's after at T2, what we are doing, Hadamard on Q1. So that means it's as of now, let me just don't write the amplitudes because this will be very big. So I will be just writing it, writing the quantum state, except the amplitude. 1 by root 2. Okay, here I have written only. No issue. Okay. So T3 will be when you will be applying the C naught gate where on Q1 and Q2. Before that, alternatively, let me just write T2 also in this way that 0, okay, in this way, say 0, 0, 0 plus this, I guess 1, 0, 0, right? 1, 0, 0. All right. Then T3 is nothing but T3 is nothing but Q1 and Q2. So this is 1 and this is 2 and this is 1 and this is 2. So C naught will be 0, 0, 0 plus 1, 1, 0. I'm not writing the amplitudes, okay? Now, till this part I'm done. T3, I'm here. So after that, I have to apply Hadamard on Q3. So this Q3 needs to be again Hadamarded, okay? So T4 will be, just check very carefully how I'm writing it, 0, 0, 0 plus, so this 0 will be 0 plus 1. So likewise, so this 0 has now become 0 and 1. And these first 2 qubit is as it is, okay? Similarly, now this 110 will now become 110 and 111. Is this thing clear? See, this 0 I have converted to 0 and 1, and these 0 also have like expanded to 0 and 1. Why? Because I am applying Hadamard on Q3 only, and this is my Q3. Absolutely, I guess it is clear for everyone. If it would be on Q2, then it would be completely different set of quantum states. Then we have to expand this Q2 wala 0 and then again here this Q2 wala 1. Both of the things we have to expand as per the Hadamard gate on H0 and H1. But right now we fortunately got 0. That's why the no negative sign came here. Okay. So now at T5 it will be what? It will be Q1, Q2 is control. Q1, Q2 control is there for the last 2 cases. So as it is, let me write first 2. Then it will be 111 plus audible now?
Yes, ma'am, you are audible.
Okay. I think meanwhile there was an issue with the internet. Okay, okay. Thank you. Thank you for confirming. Just I was here. Okay. So someone was asking about at T4. That have you like got T4? I again explained it. Okay, it got lost somewhere. Okay, so see it over here. So what I'm doing at T4, just before T4, I'm applying a header mode on Q3, right? So initially my Q3 was 0 here. This is my first, second, and third qubit, and this is my first, second, and third qubit. So for both the cases where I'm having the third qubit, I have to expand it as per the header mode here, based on the values that I have. What I have, it's already in full screen mode. It's already in full screen mode. Yes. So what I have here, I have a 0. It will be K0 plus K1, not full screen, but it's already full screen from end. For us, not. Let me again just go back and make it in a full screen format. Slideshow mode. Yes, it was on only. I don't know. Just a minute. Yes, my screen is also shared. I'm sharing my screen as well, and it is in a full screen mode. Please confirm. It's not frozen, I guess. I'm in this slide only. Saroj slideshow. Okay. I'm doing the same. How can that be? Everyone has this issue. Joined. Let me stop sharing and again start sharing. Let me just stop it and again I will do it. Just a minute. Just a minute. Can you see the screen now?
Not yet, ma'am.
Oh, I don't know why.
It's visible now, ma'am. You can continue for some time and then we can check again.
Is there any issue with my audibility? Am I audible now? Okay, let me again try it because I was checking with the issue. Yes, I know. Initially also it was audible, but why there is an issue with the screen sharing? Uh, no, that's one because I'm sharing full screen. Just a minute. Share content. Yes. Screen audio. This is good. Apply your knowledge there and you sound as student. From my end. Let me do one thing. So let me just share today's content to mail, and if possible, if someone else can just show it, then I will be like explaining it. Will it be okay, sir?
Uh,
So I'm sending it to Sir's mail ID. I have his mail ID only. Just a minute. Yes. Fine, sir. I mean, it's like multiple times I am joining and again doing this thing. YouTube lectures. Use just be a little patient, please, everyone.
Ma'am, please share your slides on the email ID which we have provided in the chat, and then share it.
Yes, I'm just trying the same. Just give me a minute. Can I just share the ID where I should be directly sending it? So
It's fdp.academy.mnit.ac. Ma'am is trying to rejoin, so let's wait for 5 more minutes, and hopefully we'll be able to resume the session. We will have this particular session till 4:20. Let's wait. So ma'am has just joined, so hopefully we'll be able to begin soon.
To the WebEx, but the screen is not being shared. I can again try once. I don't think there is certain issue either with the WebEx from my end or with the like the file that I'm trying to share. It's unable to share. So one suggestion would be, or one request would be to all the participants, if tomorrow we can make this thing up, and if you all agree, then at least either we can start from either we can start from okay. Again, it's showing. So I don't think it's visible. So anyway, I'm stopping sharing. So if tomorrow we can make it up and can manage for any of the time, like half an hour before, like 1:30 to 4, or we can make it from say 2 to 4:30. Can we do that?
I guess, ma'am, 2 to 4:30 will be better. I guess most of the participants will be also agree.
Yes. Because anyway, there is an issue. So I
Uh,
guess tomorrow, also like just before the session, I will be sending for tomorrow so that you have the like content also.
sure, ma'am.
Right?
2 to 4:30
Let's
is
plan
fine.
that accordingly.
Right, sure.
Sure. Thank you, and very sorry for this interruption. So it's almost like 4, but we are unable to
Right.
like continue with the content.
Right. So it was some
Okay.
technical error, but it's
So
fine. So we'll continue tomorrow. Thank you for the insightful session, ma'am.
thank you, everyone, for your cooperation. Thank you. Yes, I can like see queries, but unfortunately, the screen I cannot share. Okay, no issue. We will all see and exactly start from wherever we paused today. So I guess from 3:30, almost half an hour content was pending. So accordingly, we will start, and I will plan tomorrow's session. I will conclude at 4:30 tomorrow. Thank you, everyone. Thank you for joining.
Sure, ma'am. Thank you. Thank you so much.
Thank you.